Thanks for the kind introduction. Yeah, right. My name is Ari. I'm from the University of Muenster in Germany. And the next 10 to 15 minutes, I will try to encourage you to read our newest ACM TOPLAS paper, which is actually generally saying about the general fundamental formalism for expressing and optimizing data parallel computations. So, yeah, right. Before we start, just some quick introductory remarks. So, of course, this talk will very briefly highlight or actually advertise the main contribution that we are making in the paper. So I have, for example, like 20 slides to describe more than 70 pages, and I will focus on some illustrative examples rather than formal definition and details, which can all be found in the paper. I also want to mention that we have a full version of the paper uploaded on arXiv that contains really all the formal details, so that hopefully no questions are left open. And yeah, I must admit the paper is quite long, so the TOPLAS version is more than 70 pages, arXiv version even more than 130 pages. But despite the length, please, if you're interested in this topic, consider reading it. So we have many illustration and discussion, so even when skipping all the formal details, you should get at least general ideas here. And even more important than that, so this paper really tries to make a general fundamental contribution here to the community. So it helped me personally a lot to see things clearer, and I really put a lot of work in it so that it helps me, but hopefully also you guys. Okay, that one is. So, okay, the goal of this work, so actually since I started my PhD, I always had questions in my head, so even when reading fantastic related approaches, so that still remains. So, like for example, data parallelism. How can we define formally data parallelism? So we have all these different kinds of data parallel computation, let's say linear algebra routines, stencil computations, all these computations that are currently used in deep learning. We consider them all as data parallel, but often they are considered differently, expressed differently, optimized differently. And I was always wondering, what can be a formal definition where all these different kinds of data parallel computations can be are particular instances of this definition here. So the next question. Okay, if we have such a definition, what are the basic building blocks that we need to express any kind of these kind of computation to these data parallels one? So basic building blocks to express linear algebra routines as naturally as we can also express, for example, stencil computations here. And of course, we want these building blocks to be agnostic of hardware and optimization details, but still capture all information that are relevant for generating high-performing code. And the next question is, so how can we formally define optimizations for data parallel computation in general? So a general set of optimization rules that apply to any kind of data parallel computation here. Yeah, exactly. So general optimization here, that's already this question also, and the last one. Yeah, exactly. How can we structure these optimizations so that we can fully automatically explore the optimization space here? So, for example, based on auto-tuning techniques. And yeah, this paper actually aims to answer all these questions fully formally. But okay, so let's dive in. So what this paper does is it introduces a formal framework for expressing and optimizing data parallel computations based on 3 major contributions. The first one is a high-level program representation. So as part of this contribution, we define data parallelism formally, and we introduce higher order functions for expressing data parallel computations, agnostic of hardware and optimization details, and still capture all the information that we require later in our code generation process to generate code that achieves performance even competitive to hand optimized solutions here. The second contribution is introducing a formalism for expressing and reasoning explicitly about optimizations for data parallel computation. So actually, how can we make these problems smaller so that they fit into the memory and core hierarchies of state-of-the-art parallel architectures? And how can we generalize this optimization to apply to arbitrary combinations of data parallel computations and architectures? And the last contribution is, okay, we have an instance in our high-level representation. How can we fully automatically lower it to an instance in our low-level representation that's optimized for the device and also the data characteristics? So, okay, what are we going to do in the following? I will briefly just highlight and advertise our 3 main contributions. So the high-level representation, the low-level representation, and the lowering process. I will present some experimental results in terms of all performance, portability, and also productivity. Then briefly discuss related work and conclude the talk. Okay, at this point, I just want to emphasize again, so that will be actually on a very quite high level. So we have, for example, in our paper, an extensive set of experiments on more than 23 pages, while I just have 4 slides to describe the experiment. So if this talk can somehow gain your interest, the paper is much more exciting than the talk. So, okay, our high-level representation. So while we have designed our high-level representation, we had 3 major goals in mind. It should be uniform, minimalistic, and structured. So here, uniform means it should be able to express any kind of data parallel computation without relying on any domain-specific building blocks. So we don't want to have building blocks just oriented toward linear algebra and some oriented maybe towards stencil computation. And if someone comes up with a new kind of data parallel computation, we need to extend and improve our language somehow, so we want to avoid this. We want it to be minimalistic, which means we want to rely on as less building blocks as possible to keep our language simple, of course for the user who uses the language, but also for us implementers. And we want it to be structured. So structured means here we want to avoid nestings and compositions of these building blocks as much as possible to further contribute to the usability of our, or to the simplicity of our language. Again, for the user and also for us implementers. And the paper we can show that our high-level representation first defines data bulk computations as the so-called multidimensional homomorphisms that were mentioned. And it expresses data bulk computations using exactly 3 simply composed higher-order functions only. So we only need these 3 functions that you can see there on the top, infu and deum on output, to express any kind of data bulk computation according to our definition. So here, just quickly, infu is responsible for the input data. So it expresses what kind of input data are used, how they are accessed, these kind of things. And deum always and uniformly expresses the data per computation part, and outview is responsible for the output data. And the paper we could show, just using these 3 patterns, we can express a wide range of data per computation. Like, for example, linear algebra routines, where it express dot products, matrix vector multiplication, matrix multiplication, batch matrix multiplication. And yeah, actually, we could even show in the paper that these expressions naturally evolve from each other. So, for example, a matrix vector multiplication, nothing else than computing multiple dot products. That's exactly reflected in our formalism here. The same for matrix multiplication and matrix vector multiplication, and so on and so forth. But we have also, for example, expressed convolution like stencil, Jacobi stencils, which differ significantly from linear algebra routines because they access neighboring elements in their input. So they are often quite differently optimized than linear algebra routines. Then we have also expressed maximum bottom box sum, which was a running example in the PLDI paper. We have scan patterns, map-reduce patterns, histograms, probabilistic record linkage, which is used in data mining to identify duplicate entries. So there's really a wide range, and these also, these computations really define major characteristics here. So regarding our low-level representation, so just on one slide quickly. So the goals have been, we want to express in hardware and data optimized decomposition and recomposition of data per computations. So as I said at the beginning, how can we make the problem smaller, that it fits into the memory and core hierarchy of the architecture? No matter what architecture, we have an abstraction for architectures introduced in our paper here. And the second goal is, it should be straightforwardly transformable to executable program code. So for example, OpenMP for CPU, CUDA for GPU, OpenCL for multiple kinds of architectures. And straightforwardly actually means that all the major optimization decisions are already expressed in our representation. Just that you get a quick idea how it looks like, the low-level representation there. So these are just 3 phases. On the right side, you can see the decomposition, so how we make the problem smaller. In each step, we say how we assign these smaller computations to the core memory hierarchy. Then we have below what we call scalar computation, so that's usually the inherently sequential part of a computation. And then we recompose the results back. Okay, just a quick excursion. So based on the structured design of our low-level representation, we could even show that we can visualize optimizations. So we have these kind of visualizations for any kind of data per computation, and also for any kind of architecture. They are of this form. I don't want to dive into detail here, but I just wanted to mention it. And yeah, just one quick slide about code generation. So code generation is actually not the focus of our paper here, but we have outlined it in the appendix of the full version of the paper, actually. And it's based on an imperative-style pseudocode notation, and it's intended actually to be described in detail in our future work. So what I just want to say, so of course we have implemented everything, but it's not that much described in the paper and can be found in the appendix of the full version. So regarding our lowering process, so our lowering process from high level to low level is based on formally defined performance critical parameters so that we get a structured optimization process that allows fully automatic exploration of the space. So in this case, for exploration, we use auto-tuning, particularly our auto-tuning framework ATF that we have presented a couple of years ago at TACO. And so parameters don't aim to introduce some advanced new optimization here, but to unify, generalize, and combine well-proven optimization. So data movements, tiling, makes them flexible, and generalize them to apply to arbitrary data per computations here. And yeah, regarding experimental results, so we really try to make experimenting challenging for us. So we evaluate our approach in terms of performance, portability, and productivity. We try to compare to the best available solutions right now. So like, for example, Apache TVM, which is a scheduling-based approach, polyhedral compilers, PPCG for GPU, Pluto for CPU, the popular lift approach, which is based on functional concepts, and also we compared to domain-specific libraries like NVIDIA QBLAS, QDNN for GPU, and 1MCAL and 1DNN for CPU. And these are highly optimized libraries by hand at the assembly level to achieve the highest performance on the target architecture. And we also consider a bunch of different case studies here. So we have linear algebra routines, matrix multiplication, matrix vector multiplication. We have two different kinds of stencil computations, a 1D example, Jacobi, and a 2D example, Gaussian convolution. We have an example from quantum chemistry. We have this data mining example. And we also have a deep learning case study inside the experiment. And regarding our performance evaluation, so these are just some highlights, and just for the deep learning case study, because that was the most challenging study for us, because most of the competitors are highly optimized for them. So, for example, TVM is highly optimized for deep learning, and even the vendor libraries. And the performance evaluation is based on a runtime comparison. And here we can observe, for example, we achieve speedups of more than 2x as compared to TVM, and sometimes even more than 9x as compared to the hand-optimized solutions here. We have some slowdowns as compared to TVM, but these are actually mostly for a technical reason. So our implementation currently uses the NVRTC library, while TVM uses NVCC. I have no idea why NVRTC generates less efficient CUDA assembly than NVCC, but that's the reason for slowdowns as compared to TVM. So the portability evaluation in our paper is based on the so-called Pennycook matrix. So here a value close to 0 means low portability, and a value close to 1 means high portability. So for a deep learning case study, we can see that we achieve higher portability than TVM in all cases. And actually also as compared to the other approaches, which achieves the lowest portability of 0 only. That's because they are limited to particular architectures maybe, or with particular application classes. So they're not even functional portable, and that's especially not performance portable. But in the paper, we also consider just portability on GPU, CPU to make comparison for these approaches easier to us. But that's not on the slides. And the productivity evaluation is just based on intuitive argumentation in our paper. So classical code metrics like lines of code and COCOMO effort are not very meaningful for these short and concise programs as we use, and of course also the related approaches here. So regarding related work, so we could show in the paper that MDH often achieves higher performance, portability, and productivity. So we have a big discussion about that in the paper. So for example, we could show that scheduling approaches usually achieve very high performance, but they often struggle with achieving portability and productivity. So productivity mostly because they incorporate the user into the optimization process. So there must be optimizations expressed explicitly. In contrast, polyidal compilers often usually achieve very high productivity, even by optimizing fully automatically straightforward sequential code, but therefore they struggle with performance and portability. So we have a big discussion what are the reasons for this and that. I just want to briefly highlight this here on the slide. And that actually brings me to the conclusion. So the conclusion is very short here. So the two big giveaways I want to give you, so it's MD is the formalism for expressing and optimizing data per computation in general here. And that we could show that MDH achieves higher performance, portability, and productivity. So it's not just formal stuff here, it really has some relevance for practice here. And I also want to use this opportunity to make some advertisement for our website. So we have recently uploaded the website. Please feel free to check if there's somehow interesting for you. And that's actually the end of my talk. So thank you very much for listening. I'm grateful for any kind of feedback because this work is very important for us. So it can also be bad feedback, so that's fine. And I'm happy to answer questions now. We should have plenty of time left. Thank you.
Yeah, as Ari mentioned, we have time for questions. So if folks could use the mic there in the middle.
Hey, thanks for the talk. So it went by a little quick for me, but I would be very interested on your results for understanding in which cases you outperformed 1DNN, 1API, cuDNN, those sort of vendor-supplied libraries, and why specifically did you outperform in terms of like the optimization of that application?
Okay. So first of all, nothing was there cherry-picked. So these were all that I presented here, sizes used in real-world deep learning neural networks, so that for sure. The reason why we exactly outperform them, we cannot explain always with certainty because they are not open source. But one reason is we can auto-tune, for example, our code specifically for the input size. Or these approaches rely on heuristics that are optimized toward average high performance over a range of sizes. We think that that might be the reason that we achieve better performance than them. But you cannot check inside, but I think that...
Is that size tuning consistent with all the results you've seen, or I guess there's not a way
There was
to
no
test
pattern
that
in it. Sometimes you were
hypothesis,
better,
really.
sometimes not. And we have very thorough comparison. So for example, with QBLAS, we compared to all the QBLAS routines using all the algorithm stuff. We compared also to MKLJIT and these kind of things. That can be all checked in the paper. But it's mostly because of the auto-tuning, I think. These approaches, of course, they hand-optimized libraries, so the vendor libraries don't have this auto-tuning overhead that we have. But particularly for applications like deep learning, where the same implementations are reused, this auto-tuning time is usually mostly amortized.
Okay.
So it's worth it.
Thanks.
But you have this auto-tuning overhead, of course. Yeah, thank you.
Thanks. I look forward for reading the 130-page
Thank you.
version.
That was my goal.
In the meantime, I wanted to ask, what would you identify as like the remaining open challenges?
Okay, so that's just, we see this as a starting point in this direction. So we have a lot of things to do. We cannot express sparse computations. We currently just target individual data per computation. So when we have, for example, a deep learning graph where we have multiple data per computations, we currently cannot optimize across the computations. There are a lot of things, so there's still much things to do, but I think these are all extensions, not improvements. So that's a fundamental that we need to do all these things.
Okay, thanks.
Thank you.
I had one last question, maybe, unless folks have another one. What's the penny cook method, or what was it? That's the portability metric.
It was presented as the one SC workshop that people are currently using. So that's a metric that you can measure performance portability. How performance portable is the code? So when you write just one code, so if you have a value close to 1, then you can expect that on different kinds of architectures, you usually will achieve, let's say, 90% of the peak performance, for example. And if the value is lower, then sometimes you might perform good, but often also worse. So it's some formula, it's also in the paper, that compares to the best solution you have observed and also to other kinds of measurements that you made. So to get to these, so how otherwise would you assess performance portability?
So, and so what's the formula over? What are the variables? Like, do you just run it on several platforms and look at how different the performance is, or is there just a quick intuition for that?
To the approach that you have observed the best performance. Sometimes these were often the vendor libraries, the number of architectures. I have the formula not in mind, right? I must admit, I just wrote it all once down, computed it, and used it. So I'm no expert for this, but it seems to be well accepted, at least by some people. Okay.
Yeah. Okay, let's thank Ari again.
Thank you.